The expert systems era represents one of the first periods when artificial intelligence moved from academic experiments into real-world applications. This video examines what expert systems were, why they achieved early success, and why their limitations eventually became clear. Understanding this era explains both early optimism and later caution around AI deployment. Expert systems were a class of AI designed to replicate the decision-making ability of human experts in narrow domains. Rather than learning from data, these systems relied on explicit knowledge encoded as rules. Their goal was to automate expert-level reasoning in areas where knowledge could be formalized clearly. The expert systems era developed primarily between the late 1960s and the 1980s. During this time, computing power increased, and organizations sought practical applications of AI. Researchers moved beyond theoretical demonstrations toward systems intended for operational use in medicine, science, and industry. Earlier symbolic AI programs solved puzzles or toy problems. Expert systems marked a shift toward solving real problems in specific professional domains. This transition required close collaboration with human experts and a focus on practical decision-making rather than abstract reasoning alone. The core idea behind expert systems was simple in principle: capture human expertise in a form a computer could use. If experts could explain how they reasoned, those explanations could be encoded as rules and applied consistently by a machine. Then general intelligence. It included facts, rules of thumb, heuristics, and decision criteria used by professionals. Expert systems did not aim to replicate human cognition broadly, only to perform well within narrow, well-defined problem areas. An expert system typically contained a knowledge base. This knowledge base stored facts about the domain and rules that described relationships between those facts. The quality of the system depended heavily on how complete, accurate, and current this knowledge representation was. The inference engine was the reasoning component of an expert system. It applied logical rules to the knowledge base to derive conclusions. The inference engine itself was generic, meaning it could be reused across domains if the knowledge base changed. A key design principle was separating knowledge from reasoning. Knowledge was encoded as rules and facts, while reasoning logic was handled by the inference engine. This modularity allowed systems to be updated or reused more easily than earlier monolithic programs. Most expert systems relied on if-then rules. These rules specified what action or conclusion should follow when certain conditions were met. The logic was explicit and deterministic, making system behavior predictable and traceable. Forward chaining was one common reasoning strategy. The system started with known facts and applied rules to infer new facts until a conclusion was reached. This approach worked well in monitoring or diagnostic tasks where data arrived incrementally. Backward chaining worked in the opposite direction. The system began with a hypothesis or goal and searched backward for evidence to support it. This approach was useful in diagnosis, where the system tested possible explanations against observed data. Many expert systems included explanation facilities. These allowed users to see which rules were applied and why a conclusion was reached. This transparency increased trust and made expert systems appealing in domains requiring accountability and justification. Several expert systems became well known. Dendril analyzed chemical compounds, while MySyn assisted in medical diagnosis. These systems demonstrated that machines could match or exceed expert performance in carefully constrained environments. MySyn focused on diagnosing bacterial infections and recommending antibiotics. It used hundreds of rules derived from medical experts. Although never deployed clinically, it performed at a level comparable to trained physicians in controlled evaluations. MySyn's success showed that explicit rules could capture expert reasoning effectively in narrow domains. Its accuracy highlighted the potential of AI when knowledge was stable, inputs were structured, and the problem space was well understood. Expert systems worked best in domains with clear boundaries. When problems were narrow, well-defined, and governed by established principles, Rules could capture decision logic effectively. This alignment between problem structure and method was crucial to early success. Clearly defined problems reduced ambiguity. Inputs followed known formats, and outputs could be evaluated against accepted standards. This made it easier to encode expertise and verify system performance. Another success factor was access to human experts. Knowledge engineers worked closely with specialists to extract decision rules. When experts were available and cooperative, systems could be built with high-quality domain knowledge. Expert systems also benefited from predictable environments. When rules did not change frequently, systems remained valid longer. Stability reduced maintenance costs and made rule-based reasoning more reliable over time. Organizations began adopting expert systems in areas such as equipment configuration, credit evaluation, and diagnostics. These systems promised consistent decisions and reduced reliance on scarce expert labor. For businesses, expert systems offered several advantages. They standardized decision-making, reduced errors from fatigue or inconsistency, and allowed expertise to be reused across locations and shifts. Transparency was a major advantage. Because decisions were rule-based, organizations could inspect logic, audit outcomes, and explain results to stakeholders. This characteristic remains valuable today in regulated industries. Despite early success, limitations became apparent as systems grew larger. Rule sets expanded, interactions became complex, and maintaining consistency grew increasingly difficult. These issues challenged scalability. The knowledge engineering bottleneck emerged as a central problem. Extracting rules from experts was slow and expensive. Experts often struggled to articulate implicit knowledge, and translating it into formal rules required specialized skills. Updating systems proved difficult. As domains evolved, rules needed constant revision. Even small changes could require extensive rework, making expert systems fragile in dynamic environments. Expert systems were brittle. They performed well within their assumptions, but failed unexpectedly outside them. Unanticipated inputs or edge cases could lead to incorrect or nonsensical conclusions. Unlike modern learning systems, expert systems could not learn from experience. They relied entirely on predefined knowledge. Without manual updates, performance could not improve or adapt to new patterns. As rule counts increased, interactions between rules created combinatorial complexity. Reasoning became slower and harder to manage. This rule explosion limited how large and flexible systems could become. Handling uncertainty was another challenge. Early systems used ad hoc methods such as confidence scores, but these approaches were limited. Probabilistic reasoning was not yet mature enough to be integrated effectively. Expert systems depended heavily on human experts. Differences in expert opinion led to inconsistent rules. Subjectivity became embedded in systems, reducing reliability across contexts. Development costs were high. Building an expert system required years of collaboration, testing, and refinement. Many projects failed to deliver sufficient return on investment. Deploying expert systems in organizations was also challenging. Integrating them into workflows, training users, and maintaining trust required significant effort beyond technical development. Overpromising exacerbated disappointment. Some vendors and researchers claimed expert systems would generalize easily or replace professionals broadly. When this failed to materialize, confidence declined. As domains changed rapidly, static rule-based systems struggled to keep pace. This mismatch highlighted the limits of purely symbolic approaches in complex, evolving environments. By the late 1980s, enthusiasm for expert systems waned. Funding declined, projects were cancelled, and attention shifted elsewhere. This period contributed to what became known as an AI winter. The decline reflected unmet expectations rather than uselessness. Expert systems worked where assumptions held, but failed to scale broadly. The lesson was not that AI was impossible, but that intelligence was harder than anticipated. Expert systems taught valuable lessons about domain limits, knowledge representation, and system maintenance. These insights continue to inform modern AI design and deployment decisions. Many contributions endured. Rule engines, explanation methods, and structured reasoning remain relevant. Modern business rule systems inherit ideas from expert systems. Expert systems influenced modern AI by clarifying where explicit rules are useful and where learning is required. This distinction underpins today's hybrid approaches. Compared to machine learning, expert systems relied on rules rather than data. Machine learning addressed many scalability issues by learning patterns automatically, but sacrificed some transparency. Learning-based methods became necessary to handle scale, variability, and uncertainty. This shift marked a new phase in AI, building on but not replacing symbolic foundations. Expert systems were not a failure. They succeeded in narrow domains and demonstrated that parts of expertise could be formalized. Their limitations provided critical guidance for future approaches. A key lesson is to match methods to problems. Rule-based systems excel where rules are stable and explicit. Applying them outside such conditions leads to brittleness and disappointment. Expert systems still make sense in regulated or safety-critical domains with clear rules. Many organizations use hybrid systems combining rules and learning to balance reliability and flexibility. Hybrid approaches reflect continuity in AI history. New methods build on earlier insights rather than replacing them entirely. Understanding this continuity helps avoid repeating past mistakes. The expert systems era illustrates cycles of optimism and correction in AI. Each phase contributes knowledge, even when expectations must be revised. The core takeaway is that expert systems solved narrow, well-defined problems effectively, but struggled with scale and change. Their story explains both early AI success and subsequent caution. Studying this era provides perspective on modern AI claims. It reminds us to evaluate systems based on evidence, scope, and assumptions, rather than broad promises. Next, we will explore how limitations of expert systems motivated the rise of machine learning, marking a transition from rule-based intelligence to data-driven approaches that define modern AI.